Mars is the obvious next step. Everyone says so. Mars is the red planet, our nearest neighbour, the target of decades of space programs and billions of dollars of investment. SpaceX is building ships for it. NASA is designing missions. Elon Musk has staked his legacy on it. The cultural conversation around human expansion into space begins and essentially ends with Mars. And all of that makes sense. Mars is close. Mars is reachable with current or near-current technology. Mars is the logical next step if you look at a map of the solar system and choose the nearest available destination. But there is a moon that almost nobody mentions in these conversations, a moon of Saturn. Sitting 1.4 billion kilometers from Earth, 9.5 times farther from the Sun than we are, covered in orange haze, with lakes, with rivers, with rain, with weather, with an atmosphere so thick that a human being could walk on its surface in something closer to a wetsuit than a pressure suit. Titan. And tonight, we are going to make the case, honestly, specifically, with actual numbers, for why Titan changes the conversation about where humanity should go next. Not because Mars is the wrong choice, Mars is a good choice, but because Titan is the better choice, by several criteria that matter more than most people realize. And those criteria deserve honest examination. If the night is long, stay. Let us begin with the single most important number in the entire comparison, the one that rewrites the conversation before it even begins. Radiation on the surface of Mars, approximately 200 to 300 millisieverts per year. Radiation on the surface of Titan, approximately 5 to 6 millisieverts per year. Let that difference sit for a moment. The annual radiation dose on the surface of Mars is roughly 50 times higher than on the surface of Titan. 50 times. Not 10% more, not twice as much. 50 times. For context, the annual radiation dose for a person on Earth's surface, about 2 to 3 millisieverts. The career limit for NASA astronauts, about 1,000 millisieverts total. The dose at which acute radiation sickness begins, about 1,000 millisieverts in a short time. The annual dose on the ISS, about 150 to 200 millisieverts. Already 50 to 100 times Earth's surface. The annual dose on Mars, 200 to 300 millisieverts, similar to the ISS, significantly above any reasonable long-term occupational limit. The annual dose on Titan, 5 to 6 millisieverts, comparable to a few CT scans, below the threshold that requires any specific protective measures, manageable. Why is Titan's radiation so low? Because of its atmosphere. Titan's atmosphere is 1.5 times denser than Earth's. It is predominantly nitrogen, 95% nitrogen, similar to Earth's atmosphere. This thick blanket of gas absorbs and scatters the high-energy particles that would otherwise reach the surface. Cosmic rays, solar particles, energetic protons and electrons. The atmosphere does what the ISS's partial magnetospheric shielding does, but better. And it does it for free. It requires no engineering, no buried habitat, no radiation shelter dug into the regolith. It is simply there as a property of the Moon itself. On Mars, there is no such protection. Mars lost its global magnetic field roughly 4 billion years ago. Its atmosphere is about 100 times thinner than Earth's. The surface is exposed. Any long-term Mars habitat must be built underground or buried under meters of regolith specifically to manage the radiation that the atmosphere cannot block. This is not a minor engineering detail. Digging underground habitats, maintaining them, working from them, this is a fundamental constraint on what human life on Mars looks like. It means residents of Mars live like moles, venturing to the surface only with substantial radiation risk management. Residents of Titan could live at the surface, in structures that are not radiation bunkers, with excursions outside that are not radiation emergency events. This single difference changes what long-term human presence looks like more than almost any other factor. Let us now talk about the second number that rewrites the comparison, about atmospheric pressure and what it means for the engineering of survival. Atmospheric pressure on Mars about 0.006 atmospheres, 6/1000ths of Earth's surface pressure. Atmospheric pressure on Titan about 1.5 atmospheres, 50% more than Earth's. These numbers create profoundly different engineering problems. On Mars, the pressure suit is the central engineering challenge of human presence. A person inside a suit at 0.3 atmospheres internal pressure, surrounded by 0.006 atmospheres external pressure, experiences a differential of about 0.294 atmospheres pressing outward from inside the suit. This inflates the suit. The suit becomes stiff. Movement is constrained. The suits used by Apollo astronauts on the Moon, facing complete vacuum, maximum differential, were famously difficult to work in. Astronauts described them as exhausting to move in. Hands became sore from fighting the suit's pressure to close fingers around tools. Mars suits face a nearly identical problem. The outside is almost vacuum. The suit must hold significant internal pressure and does so by becoming rigid and balloon-like. On Titan, the engineering is reversed. Inside the suit, perhaps 1.0 atmosphere, outside 1.5 atmospheres. The external pressure is higher than the internal pressure. The suit is being compressed, not inflated. A suit under external compression can be soft and flexible, like a wetsuit or a thick winter jacket, rather than a rigid, inflated structure. This means a Titan suit can, in principle, be much more like a garment and much less like a spacecraft. The primary engineering challenge becomes thermal insulation, keeping a person warm at -179 degrees Celsius, not pressure containment against vacuum. Thermal insulation is a solved problem in a way that pressure containment in vacuum is not. We make excellent thermal insulation. Sleeping bags keep people warm at extreme temperatures. Expedition suits for Antarctic researchers maintain body temperature at -60 degrees. Scaling to -179 is a significant engineering step, but it is a step in a direction where the physics is understood and solutions exist. This distinction, pressure suit versus thermal suit, is not trivial. It affects mobility, energy expenditure during surface work, suit durability and repairability, the psychological experience of being outside, and the engineering resources required to develop and maintain suitable equipment. A person working outside on Titan is in a different physical and psychological situation than a person working outside on Mars. One is fighting an inflated balloon with every movement. The other is wearing very good winter clothes. Let us now talk about something that most comparisons of Mars and Titan get wrong, about the actual experience of living there for years, not visiting for days. Human beings are not optimized for survival. We are optimized for flourishing. The difference matters enormously when considering multi-year or permanent habitation of another world. Survival requires food, water, breathable air, temperature management, and protection from immediate physical threats. Any minimally adequate habitat achieves this. Flourishing requires space, variety, meaningful activity, social connection, a sense of connection to a living environment, psychological engagement with the world outside the walls of the habitat. Long-duration missions, Antarctic winter rovers, submarine deployments, simulated Mars missions consistently show that psychological deterioration, not physical deterioration, is the primary threat to crew performance and well-being during extended isolation. The third quarter effect, the psychological low point at 60 to 75% of a mission's duration, is documented across every type of extended isolated mission. It manifests as declining motivation, increasing interpersonal friction, reduced capacity for complex decision-making. On Mars, the psychological environment is harsh. Any surface excursion requires a full pressure suit with radiation risk. Visibility is limited by dust storms periodically. The landscape is a mineral desert, geologically interesting to scientists, but visually monotonous in its redness and emptiness. The sky is brown-orange by day, fading to blue near the horizon at sunset. No rain, no rivers, no large-scale fluid dynamics. No weather that does anything beyond blow dust and occasionally freeze the CO2 in the atmosphere. On Titan, the psychological environment is radically different. Rain falls. Not metaphorically, literally. Methane rain from methane clouds falls onto the surface of Titan. Rivers run. They flow toward the hydrocarbon lakes and seas that fill the northern polar region. Waves form on the seas. Shorelines exist. The landscape is varied. Massive sand dunes made of organic particles cover the equatorial regions, dark, structured, swept into parallel ridges by the persistent low-level winds. Icy plains stretch between them. Impact craters, few because the atmosphere burns up most impactors, exist as distinct geological features. The northern polar region is a complex hydrological landscape of bays, peninsulas, rivers, deltas, and open liquid surfaces. The sky is orange with photochemical haze. The sun is a dim, blurry disk rather than a blinding point. It is not beautiful in the way a clear blue sky is beautiful, but it is not dead either. It has texture. It changes with altitude. The haze layers at different heights create a structured visual environment. Dragonfly, the NASA mission launching in 2028, will give us the first ground-level views of this environment. Not from orbit, not from a high-altitude flyby, from the surface, looking out as a person would look out. What those images show will change how we imagine Titan forever. For a person living on Titan, the outside world, while cold, is accessible. Not a radiation emergency, not a pressure engineering challenge. A cold walk in very good insulation, in a thick atmosphere, in a world that has weather and rivers and seasons. This is not nothing. For the psychology of long-duration habitation, this is enormous. Let us now talk about the third number that changes the comparison, about what the atmosphere means for transportation across the surface. Getting around on Mars is a wheel problem. You drive. The Mars rovers drove. Future human explorers will drive pressurized rovers. The terrain is navigable, rocky but not dramatically different from terrestrial desert terrain in terms of what a wheeled vehicle can handle. But driving has limitations. Range is constrained by battery or fuel capacity. Obstacles that block a wheeled vehicle cannot be bypassed. Interesting scientific targets that are in terrain inaccessible to wheels are simply unreachable. Ingenuity, the helicopter NASA deployed with Perseverance, changed this. It demonstrated that flight on Mars is possible. But it demonstrated it with extraordinary difficulty. The atmosphere of Mars is about 0.6% the density of Earth's at sea level. To generate enough lift to fly in this near vacuum, Ingenuity has rotor blades that are much larger than its body size, spinning at 2,400 revolutions per minute, far beyond what comparable Earth rotors would require. It weighs 1.8 kilograms and carries essentially no payload beyond its own sensors. Every flight is a technical achievement. On Titan, the mathematics of flight is inverted. Titan's atmosphere is 4 times denser than Earth's at sea level. Its gravity is 0.14 g compared to Earth's 1 g. The lift generated by a rotor at a given speed is proportional to air density. The weight that must be overcome to lift a vehicle is proportional to gravity. At Titan's air density and gravity, the same rotor moving at the same speed generates about 28 times more net lift relative to the weight being lifted than on Earth. Flying on Titan is not a technical challenge. It is the default mode of efficient transportation. This is why Dragonfly is a rotorcraft. Not because NASA wanted to try something exotic, because for Titan, flight is the obvious choice. A rover on Titan would be the exotic choice, and the implications extend beyond the robotic mission. For human transportation on Titan, personal flying vehicles, aerial platforms, rapid transport between distant locations, all of these become realistic options at reasonable engineering costs. On Mars, aerial transport is a specialized and expensive capability. On Titan, it is the natural and efficient mode. Consider what a Titan outpost looks like if its residents can fly to neighboring locations routinely. Scientific range expands enormously. Geological survey of nearby features does not require weeks of driving. Emergency response between habitats can happen quickly. The psychological benefit of the ability to travel, to visit different environments, to see different landscapes, is significant for long-term habitation. Flight changes what the surface of Titan is. It makes it navigable in a way that no other world in the outer solar system is navigable for humans. Let us now talk about the organic chemistry, about what makes Titan's surface unique in the solar system, and why this matters for both science and long-term human presence. The atmosphere of Titan is a chemical factory. Ultraviolet light from the Sun and energetic particles from Saturn's magnetosphere break apart methane and nitrogen molecules in the upper atmosphere. The fragments recombine into increasingly complex molecules: ethane, acetylene, propane, hydrogen cyanide, benzene, and eventually the sticky orange particles called tholins that give Titan its distinctive color. These tholins settle out of the atmosphere and coat the surface. The equatorial dune fields, vast parallel ridges of dark material swept by Titan's winds, are made primarily of organic particles. The coastal regions around the hydrocarbon seas contain sediment carried by rivers. The entire surface is draped in a layer of complex organic chemistry that has been accumulating for billions of years. The chemical diversity of Titan's surface exceeds that of every other body in the solar system except Earth. We have not sampled it. We have inferred its richness from spectroscopic observations and atmospheric chemistry measurements. But the diversity is real and is a direct consequence of the same nitrogen-methane photochemical system that produces Titan's signature haze. Why does this matter for science? Because these are prebiotic molecules. The same classes of compounds, amino acid precursors, nucleobase precursors, complex nitrogen-containing organics, that appear to have been present on early Earth before life emerged. Earth's prebiotic chemistry is gone. 4 billion years of geological activity, water cycling, and biological processing have erased the record. We cannot directly study what the chemistry of life's precursors looked like on early Earth because it no longer exists. On Titan, it does exist. The cold temperatures preserve it. The lack of liquid water prevents it from being processed further. The thick atmosphere shields it from the destructive UV that would break it down on an airless body. The surface of Titan is a preserved sample of prebiotic organic chemistry operating over billions of years. Dragonfly's primary scientific mission is to analyze this chemistry. Its mass spectrometer, DRAMS, is designed to identify specific organic molecules with the sensitivity to detect amino acids and nucleobases if they are present. It will fly to multiple geologically distinct regions to sample different chemical environments. The results will either show what happens to prebiotic chemistry without life, a control experiment for the origin of life that cannot be done anywhere else, or will show signatures of biology that would represent the most significant scientific discovery in human history. Why does this matter for long-term human presence? Because organic chemistry is the basis of materials science, agriculture, and industrial production. A civilization that has access to vast quantities of diverse organic compounds has raw material for plastics, lubricants, pharmaceuticals, construction materials. On the Moon, there is no organic chemistry. On Mars, there is trace organic chemistry degraded by UV and perchlorates. On Titan, organic compounds are literally everywhere, preserved and abundant. A long-term human presence on Titan would not need to import organic industrial feedstocks from Earth or synthesize them from scratch. They would find them on the surface, ready to be processed. Let us now talk about something that is rarely discussed in the Mars-Titan comparison, about the meteorological environment and how it differs from every other destination we consider. Weather exists on several solar system bodies. Venus has weather, intense, corrosive, crushing, dominated by sulfuric acid clouds and surface temperatures of 465 degrees Celsius. Jupiter has weather, the most violent in the solar system, with wind bands at different latitudes moving at different speeds for centuries. Mars has weather, dust devils, dust storms, seasonal pressure changes. Titan has weather that is comprehensible to a human being. Methane evaporates from the surface and the seas. It rises into the atmosphere. It cools and condenses into clouds. The clouds produce rain. The rain falls on the surface. It collects in rivers. The rivers flow to the seas. This is a hydrological cycle. Different working fluid, methane instead of water. Different temperature, -179 instead of +15. But structurally, the same kind of cycle that Earth's water system follows. Cassini observed direct evidence of this cycle. Cloud systems forming over the equatorial regions following periods of rain. River networks carved into the terrain by fluid flow. Seasonal variation in the size and appearance of the northern seas as methane evaporates in summer and accumulates in winter. Titan has seasons. Saturn's orbital period is 29.5 years, giving each Titan season about 7.5 Earth years. When Cassini arrived in 2004, northern winter. When Cassini ended in 2017, northern summer approaching. The difference was measurable. The clouds were in different places. The seas had different appearances. For a human being, a world with weather is a world that is alive in a way that geological activity alone does not provide. Rain has a psychological resonance that dust storms do not. The sound of rain on a habitat surface, the visual change in the atmosphere before a storm system approaches. These things engage the human sensory and emotional system in ways that connect to billions of years of evolutionary history in a world that also had rain. On Mars, the weather is dust. The sound of Mars wind is a thin whisper. The sky changes color through dust content, but in a way that speaks of geological process rather than a meteorological one. It is interesting, it is not alive. On Titan, rain falls. That word, rain, carries weight that is difficult to fully articulate but is real. Let us now talk about the specific scientific mission that is happening right now, about Dragonfly and what it will actually do and what it is designed to find. Dragonfly is a multi-rotor aircraft, 8 rotors, 450 kilograms, significantly heavier than the Curiosity rover. It can take off, fly tens of kilometers, land, sample the surface, analyze samples chemically, then take off and fly to the next location. The primary landing target is the Shangri-La dune fields, dark organic dunes near the equator. Dragonfly will spend its early operational period characterizing the organic chemistry here. These dunes represent accumulated tholin chemistry that has been processed by Titan's atmospheric reactions over billions of years. From Shangri-La, Dragonfly will fly progressively northward toward the Selk impact crater. This is the mission's highest priority scientific target. Selk crater is about 90 kilometers in diameter. When the impactor hit, it melted the water ice that makes up a significant fraction of Titan's icy crust. Liquid water was present at Selk for potentially thousands of years after the impact. During that time, water was in contact with the organic surface chemistry of Titan. Water plus organics plus energy plus time. This is the recipe for prebiotic chemistry on Earth. At Selk crater, this experiment ran for thousands of years, and the products have been frozen since. DRAMS, Dragonfly's mass spectrometer, is specifically designed to look for amino acids, the building blocks of proteins, nucleobases, the building blocks of DNA and RNA, complex polymers, long-chain molecules that might indicate more advanced prebiotic organization, chirality signatures, whether molecules occur in the equal left-right mixture characteristic of non-biological chemistry, or in the one-sided preference characteristic of biology. If Selk crater's chemistry shows amino acids and nucleobases in chiral excess, this is the signature of biology. If it shows them in racemic mixture, this is the result of chemical evolution without biology. If it shows neither, this constrains the conditions under which prebiotic chemistry can reach biological complexity. Each of these results tells us something profound, not about Titan specifically, about the origin of life universally. The 175 kilometers of surface that Dragonfly will cover in its 2.7-year primary mission is unprecedented for an outer solar system lander. Opportunity covered 45 kilometers in 15 years on wheels. Dragonfly will cover nearly 4 times that distance in less than a fifth of the time, because flight is the right transportation mode for this world. Let us now talk about the comparison that most people make and why it understates the difference, about the actual timescales of human missions to each destination. Mars. The trip takes about 6 to 9 months one way using current or near-term propulsion. This is the transit time for chemical rockets on Hohmann-like transfer orbits. The launch windows occur every 26 months when Earth and Mars align. A minimum time crewed Mars mission, launch, transit, surface stay, return transit, is in the range of 2.5 to 3 years total. Titan. The trip takes about 6 to 7 years one way with current or near-term technology. This is the transit time for missions using gravitational assists, flying by Venus, Earth, or Jupiter to pick up speed without burning propellant. Cassini used this approach, taking 6.7 years to reach Saturn. A crewed Titan mission with such a long transit would be extremely challenging from physiological and psychological standpoints. This is the most honest argument for Mars over Titan in the near term. The trip is shorter. It is more compatible with human physiology for the duration of transit. It requires less radiation shielding for the voyage. It requires less psychological management of prolonged isolation. But this transit time disadvantage is not fixed. Nuclear thermal propulsion, which uses a nuclear reactor to heat propellant rather than burning it chemically, can roughly double the specific impulse, fuel efficiency, of a rocket. This does not straightforwardly halve the transit time because the relationship between propulsion efficiency and trip time is complex, but it significantly changes the optimization. With nuclear thermal propulsion, a crewed Titan mission timeline might shrink to 3 to 4 years each way, still long, but in a different category. NASA is actively developing nuclear thermal propulsion. The Draco program, demonstration rocket for agile cislunar operations, is intended to demonstrate nuclear thermal propulsion in the 2020s. If this technology matures, the argument that Titan is impractically far evaporates substantially.
And for robotic precursor missions, which must precede any crewed mission, the trip time is not the limiting factor. Dragonfly is spending 6 years in transit. This is fine. Robots do not suffer psychologically from long voyages. Let us now talk about the economic argument, about what the resource environment of each destination implies for long-term sustainability.
A human settlement on Mars requires, at minimum, water, present as ice, extractable, oxygen, can be produced from atmospheric CO2, demonstrated by MOXIE, food, not presently available on Mars, must be grown in controlled environments, building materials, regolith, available but limited, energy, nuclear or solar. Solar is feasible because Mars receives about half Earth's solar constant. The Martian surface has a fundamental problem for agriculture: perchlorates. These toxic chlorine compounds are present in the regolith at concentrations that are harmful to plants and to humans if ingested. Earthly organisms evolved to deal with the perchlorates present in Earth soils, which are dramatically lower than on Mars. Growing food in Martian soil requires extensive chemical treatment to remove perchlorates, or hydroponics using imported or synthesized growing media. This is solvable, but it is a significant barrier that adds to the resource cost of any Martian settlement.
On Titan, water is present as ice, extractable and abundant. Oxygen can be produced by electrolysis of water. Food, hydroponics in enclosed growing environments, faces no perchlorate problem, because Titan's surface chemistry, while exotic, does not include the oxidizing perchlorate compounds found in Martian regolith. Energy. Solar is not viable, sunlight 90 times weaker than Earth's. Nuclear is required and is available. The additional resource that Titan has which Mars lacks: surface organic chemistry in vast quantities. The tholins and hydrocarbon compounds that cover Titan's surface are raw material for organic synthesis: plastics, lubricants, solvents, pharmaceuticals. A settlement on Titan has a local organic chemical industry, available in principle in a way that a Martian settlement does not. This is not a decisive advantage in the short term. The first outposts on either world will be too small to use industrial chemical production. But in the multi-generational vision of sustainable off-world presence, the resource base matters. Titan's organic surface chemistry is an asset that has no Martian equivalent. Let us now talk about the biological question, about what Titan might tell us about the nature of life, and why this makes it scientifically unlike any other destination. The question of whether life exists on Titan is scientifically serious, not certain, not probable in the eyes of most astrobiologists, but serious, meaning it cannot be ruled out, and it deserves direct investigation. The proposed metabolic pathway for Titan life. Organisms would consume hydrogen and acetylene from the atmosphere, producing methane. This is an exothermic reaction. It releases energy that an organism could use. The organisms would use liquid methane as a solvent instead of liquid water. Their biochemistry would be fundamentally different from Earth life in its molecular basis.
Cassini found 2 pieces of suggestive evidence. First, hydrogen concentrations near the surface were lower than models of atmospheric chemistry without biology predicted. Second, acetylene appeared to be depleted near the surface relative to what would be expected from purely abiotic processes. These are not proof of life. There are abiotic explanations for both observations, but they are exactly the observations you would expect from methane-based metabolism operating at Titan's surface, which means they cannot be dismissed. Dragonfly's surface chemistry analysis will investigate this directly. If the surface organic chemistry shows biological signatures, chiral excess, complex polymers, unusual chemical ratios, this elevates the possibility significantly. If it does not, it constrains the conditions under which methane-based life could operate. Either result advances the most fundamental question in astrobiology.
Is life a singular event in the history of the universe, or a recurring phenomenon that emerges wherever chemistry and energy allow? Mars may answer a version of this question. Evidence of past microbial life in Mars's wet, ancient period would be revolutionary. But Mars's potential for life is almost certainly in the past, not the present. The Mars of today is cold, dry, and oxidizing, not an environment where we expect active biology. Titan's potential for life, if it exists, is in the present, active, ongoing, something we might actually detect rather than infer from ancient rocks. Finding life on Titan would be the most important discovery in the history of science. Finding no life but the chemical signatures of very advanced prebiotic chemistry would be the second most important. Finding basic prebiotic chemistry without further development would be the third. There is no outcome of Titan investigation that is not enormously significant. Mars, for all its scientific interest, cannot make the same claim. Let us talk about something that the Mars conversation almost never addresses honestly, about what the surface of Mars is actually like to live on for years, not to visit for days. The popular image of Mars is dramatic. Vast canyons, towering volcanoes, ancient riverbeds, the largest mountain in the solar system, the longest canyon system. These features are real, and they are extraordinary. But they are geological features. They exist at scales of hundreds and thousands of kilometers. From the surface, from human eye level, Mars is a flat, rocky plain in every direction that any Mars lander or rover has ever seen. There is no canyon visible from the floor of Valles Marineris, because Valles Marineris is 7 kilometers deep and 4,000 kilometers long. You see walls, not canyon. There is no view of Olympus Mons from the surface because it is so large, 600 kilometers wide, that the curvature of Mars hides it below the horizon. The experience of being on Mars, at human eye level looking out, is a rock field. Different rock fields in different locations. Some red, some orange, some brown, occasionally a dust devil in the distance. The sky is salmon pink to brownish orange, depending on dust content. The Sun is a small disk, noticeably smaller than from Earth, providing roughly half Earth's sunlight. No rain, no rivers, no large bodies of water, no organic chemistry on the surface, no weather in the sense of a dynamic fluid system creating varied conditions. For a scientist visiting Mars for months, this is an extraordinarily rich environment. There is geology to understand, samples to collect, subsurface to probe, ancient climate to reconstruct. For a person living on Mars for years, this is a monotonous visual environment. The rock field outside the habitat window is the same rock field it was yesterday and will be the same tomorrow. The pink sky is the same pink sky. There is no visual change that is not the result of human activity. This is not fatal to the Mars case. Human beings adapt. People live happily in monotonous visual environments on Earth, deserts, polar regions, submarines. The psychological challenge is real, but manageable. But it is worth being honest about what the surface experience is. Titan's surface experience is different. Not necessarily more comfortable, it is far colder, but visually and atmospherically richer in specific ways. The orange haze gives the sky texture that changes with altitude and atmospheric conditions. It is not a clear blue sky, but it has structure, gradients, a sense of depth that a perfectly uniform sky lacks. The dune fields are dynamic, shaped by wind, periodically modified by rare rainfall events, composed of dark organic material that has a different texture and appearance from silicate rock.
Organic sand dunes are not a thing that exists anywhere else we can study. The approach to the northern seas, which Dragonfly will eventually reach in extended mission scenarios, offers the possibility of a human settlement sited near a body of liquid with a visible shoreline, waves, and a horizon over open liquid rather than over rock. This matters. It matters for the long-term psychology of people who live there. It matters for the sense of being in a world rather than a testing facility. Let us now talk about something that is rarely quantified in the Mars-Titan discussion, about the actual engineering difference between a Mars suit and a Titan suit, and what that means for daily life. The Apollo suits weighed about 81 kilograms on Earth, 14 kilograms on the Moon in terms of felt weight.
They were stiff, difficult to move in, and exhausting to work in for extended periods. Astronauts spent enormous physical energy just fighting the suit's inflation pressure to close their hands around tools. Current Mars suit concepts, like NASA's XEMU, have improved considerably through engineering advances since Apollo, but they still must address the fundamental pressure differential problem: maintain internal human-compatible pressure against near-vacuum external pressure. The suit must be structurally capable of holding this pressure differential across its entire surface. This creates stiffness. It creates fatigue. It creates engineering complexity in every joint and seal. The XEMU weighs about 140 kilograms on Earth. On Mars, at 0.38 g, it feels like about 53 kilograms. Still significant, still affects mobility, still requires significant physical strength to operate effectively. A Titan thermal suit, designed for the main challenge of thermal insulation rather than pressure containment, could in principle be much lighter and more flexible. The external pressure of 1.5 atmospheres pressing inward actually helps the suit maintain its shape rather than working against it. The best analogy might be a highly insulated dry suit used by cold water divers. Such suits are flexible, allow relatively natural movement, and maintain the wearer at tolerable temperatures in extremely cold water. Adapting this concept to -179 degrees Celsius in a nitrogen atmosphere is a significant engineering challenge, but a challenge in the direction of insulation rather than pressure containment. The mass budget for a Titan thermal suit might be considerably lower than for a Mars pressure suit. The mobility might be considerably greater. The energy expenditure of working in it might be significantly less. For people who live on another world for years, the difference between spending 6 hours in a suit that fights you and 6 hours in a suit that moves with you is a quality of life difference that compounds across thousands of surface excursions. Let us now talk about a specific and largely overlooked advantage of Titan that has enormous practical implications, about what the presence of atmospheric nitrogen means for agriculture. Plants need nitrogen. Earth's atmosphere is 78% nitrogen, a vast reservoir that bacteria can convert into plant-usable nitrates through nitrogen fixation. This nitrogen cycle is fundamental to Earth's agriculture. It is why the Haber-Bosch process, industrial synthesis of ammonia from atmospheric nitrogen, is considered one of the most important inventions in human history, enabling the production of nitrogen fertilizer that feeds roughly half the world's current population. On Mars, the atmosphere is 95% carbon dioxide, with about 2.6% nitrogen. The nitrogen is there, but the total atmospheric pressure is so low, 0.006 atmospheres, that the partial pressure of nitrogen is about 0.00016 atmospheres. This is too low for nitrogen fixation to function at useful rates in biological systems. Producing nitrogen fertilizer on Mars requires either importing it, synthesizing it chemically from atmospheric nitrogen at low efficiency, or developing specialized biological systems. On Titan, the atmosphere is 95% nitrogen at 1.5 atmospheres total pressure. The partial pressure of nitrogen is about 1.425 atmospheres, thousands of times more than on Mars. Nitrogen is available in industrial quantities at the surface as a free gas. For a long-term settlement on Titan with agricultural ambitions, nitrogen is not a resource problem. It is ambient.
Nitrogen fertilizer production from atmospheric nitrogen is feasible using biological or chemical means at pressures that make the processes efficient. This sounds technical. The implication is straightforward. Feeding people on Titan in the long run has one less critical resource bottleneck than feeding people on Mars. The most important nutrient for plant growth comes free with the atmosphere. Let us now talk about what the specific comparison of Dragonfly and the Ingenuity helicopter reveals about the fundamental difference between Mars and Titan for flight, because this comparison makes the physics concrete in a way that numbers alone sometimes don't. Ingenuity weighs 1.8 kilograms. Its rotor blades span 1.2 meters. It spins them at up to 2,800 revolutions per minute. It can carry no scientific payload beyond its own sensors and a small camera. Each flight lasts about 3 minutes maximum. Its flights are carefully pre-planned on Earth and uploaded before execution. Its first flight on April 19, 2021 was front-page news around the world. The entire field of planetary science watched it with intense attention because no one was certain it would work. It worked, barely, and only through extraordinary engineering effort to produce a vehicle that could generate enough lift in the near-vacuum Martian atmosphere. Dragonfly weighs 450 kilograms. Its rotors span about 3.4 meters total across 8 blades. It will fly for approximately 30 minutes per flight, covering up to 8 kilometers. It carries multiple scientific instruments, including a full mass spectrometer, a suite of cameras, a seismometer, meteorological sensors, and a drill for surface sampling. Its flights are planned with some autonomy. The vehicle makes landing site decisions based on its own sensor data. The difference between a 1.8 kilogram drone that makes planetary science history just by lifting off and a 450 kilogram rotorcraft that carries a full science laboratory and autonomously chooses where to land, this difference exists because of the fundamental difference in atmospheric density. Ingenuity is the maximum that is currently achievable on Mars, given the near-vacuum atmosphere. Dragonfly is not the maximum achievable on Titan. It is a conservatively sized first mission. Future Titan rotorcraft could be larger, carry more, fly farther, operate for longer. The trajectory of aerial exploration on Mars runs into a hard atmospheric density ceiling very quickly. The trajectory of aerial exploration on Titan has enormous room to grow. This is not because Titan engineers are smarter or NASA is more generous with budgets. It is because the atmosphere is 400 times more supportive of flight relative to the gravitational field. Let us now talk about something that is both scientifically important and viscerally captivating, about what the Huygens probe's descent in 2005 actually told us about what it is like to fall through Titan's atmosphere. The Huygens probe entered Titan's atmosphere on January 14, 2005, at about 6 kilometers per second. The heat shield slowed it through aerobraking. Parachutes deployed, and then, for 2 hours and 27 minutes, Huygens fell slowly through the atmosphere of Titan, transmitting data the entire way. The data it returned was unprecedented in detail. Wind speeds at different altitudes, strong eastward winds at 120 kilometers altitude, about 100 meters per second, gradually diminishing toward the surface, where winds were 1 to 2 meters per second. Temperature dropping with altitude in a pattern that confirmed theoretical models. Methane humidity, The atmosphere near the surface was close to saturation, like a foggy day on Earth. The surface contact, when it came, was unexpected. The probe's accelerometer registered a brief bounce and then stable contact. The surface material was not solid rock and not liquid. It was something between, behaving like wet sand or soft clay. Rounded ice pebbles surrounding the landing site showed evidence of erosion by fluid flow. They had been tumbled and worn smooth by methane rivers or lake waves. Huygens survived the landing and transmitted data from the surface for about 72 minutes before its batteries died and its relay to Cassini passed beyond the horizon. In those 72 minutes, a human-made object sat on the surface of Titan, 1.4 billion kilometers from Earth, and told us what it felt and saw and measured. What it told us: the atmosphere smells. In the chemical sense, Huygens had a gas chromatograph mass spectrometer, like complex organic chemistry. The surface is cold, soft, composed of ice and organic material. The wind at the surface is gentle. The pressure is comfortable. The chemistry is extraordinary. If a person had been sitting where Huygens sat, in a Titan thermal suit, they would have been surrounded by rounded ice pebbles in an organic soil, looking at an orange-tinged foggy sky, breathing their own oxygen supply, feeling the gentle low-gravity pull of 0.14 G. In about 1.5 atmospheres of nitrogen, they did not need to worry about. Cold, very cold outside the suit, but survivable, manageable, not immediately lethal in the way that Mars's radiation or the Moon's vacuum is. This is the thing that does not come across in most descriptions of Titan. The cold is real and severe and requires engineering solutions. But cold is a thermal engineering problem with known physics. It is not a fundamentally different category of challenge from pressure containment or radiation shielding. It is a challenge in the direction of insulation, and we are very good at insulation.
Let us now talk about the specific time frame in which we will actually have enough data from Titan to make serious decisions about human exploration, about what Dragonfly's mission timeline means for the longer-term conversation. Dragonfly launches in 2028. It arrives at Titan in 2034. Its primary mission is approximately 2.7 years, through approximately 2037. Science data returns throughout this period, being analysed by scientists worldwide. By approximately 2037 to 2040, we will have detailed chemical characterization of Titan's surface organic chemistry in multiple geologically distinct regions, ground-level weather data, atmospheric structure data at the surface, seismic data about Titan's interior, detailed imagery of the surface at human eye scale from multiple locations across several hundred kilometers of traversed ground, direct chemical search results for amino acids, nuclear bases, and chiral signatures at Selk crater and the Shangri-La dune fields.
This data will define the next question. If amino acids are present at Selk, the next question is whether they are biologically produced. If the dunes show specific complex organic polymers, the next question is their detailed structure. If seismic data reveals an internal ocean, the question of that ocean's habitability becomes concrete. A follow-on mission could launch in the late 2040s, arriving in the mid-2050s, to address those next questions. This could be a more sophisticated lander with longer operational life, a subsurface probe, or an aerial vehicle with a sample return capability. By approximately 2060, we would have data from 2 missions, spanning roughly 25 years of Titan science, sufficient to make a serious engineering and programmatic case for either a robotic sample return from Titan or the beginning of conceptual work on crewed mission architecture. A crewed mission in the 2070s to 2080s is optimistic, but not impossible. if this program proceeds and if nuclear propulsion matures as expected. This timeline sounds long, but the Apollo program was proposed in 1961 and achieved its goal in 1969, 8 years with extraordinary national mobilization. The Perseverance rover mission was proposed and approved in the early 2010s and landed in 2021. Large space programs take 10 to 20 years from concept to execution. The Titan human exploration program that lands people in the 2070s needs to begin serious conceptual development in the 2030s and 2040s. Which means the scientific and public conversations about why Titan deserves this investment need to happen now, in the 2020s, while the policy and funding decisions are still open. Let us now talk about something that is philosophically important, about what choosing Titan instead of or after Mars says about the kind of civilization we want to be. Mars exploration is the exploration of a dead or dying world. Mars was once wet. It had rivers, lakes, possibly an ocean. It may have had life. All of that is over. The exploration of Mars is archaeological. We are looking for evidence of what once was. This is enormously valuable. Understanding what happened to Mars, why it lost its atmosphere and its water, what killed whatever life may have existed there, helps us understand planetary evolution and potentially our own planet's future. But it is looking backward. Titan exploration is the exploration of a world in process. The chemistry happening on Titan's surface right now, the tholin production, the methane cycle, the interaction of organics with the rare water environments created by impacts, this chemistry is ongoing. We can observe it in real time. We can watch what happens, not just what happened. If life exists on Titan, it is alive today, not a fossil, not a trace.
Alive, metabolizing, responding to its environment. This is forward-looking science. Science about what is happening, not just what happened. Science about possibilities, not just about history. The choice between Mars and Titan is, in this framing, a choice between archaeology and biology, between understanding the past and observing the present. Both have value, both deserve investment. But in the long sweep of human aspiration, in the question of where we are going rather than where we have been, the living world has a claim that the dead or dying world cannot make. Let us now talk about something that connects all of this to the specific night sky above you, about what you can actually see and what that means knowing everything we have discussed. Saturn is visible from Earth for roughly 10 months of every year. It does not twinkle. Planets, being extended disks rather than point sources, average out atmospheric scintillation. Saturn's light is steady and golden white.
Through binoculars in good conditions, you can see that Saturn is not round. The rings create ears on either side of the disk. This is what Galileo saw in 1610 and described as a triple planet. He did not understand that they were rings. Through a small telescope at 50 to 100 times magnification, the rings are unmistakable. The Cassini division, the gap between the A and B rings, is visible under good seeing conditions. The planet's disk shows subtle cloud banding, and near the planet, a small point of light that shifts position from night to night. Titan. That point of light is a world where it is raining right now, where rivers are flowing, where organic chemistry 4 billion years in the making coats every surface, where a rotorcraft launched by humans in 2028 is on its way, where the first ground-level images of a thick atmosphere organic world will be transmitted in 2034 and will change how we imagine other worlds forever. And where, sometime in the 2070s or 2080s, if we make the right decisions in the next decade, the first humans to set foot on a moon of the outer solar system will step out of a lander into 1.5 atmospheres of nitrogen, see an orange sky for the first time, and feel methane rain on their suits. That point of light next to Saturn. It is not just a moon, it is the mirror of our own origins, the place where the chemistry that became us is still running, preserved in amber-like cold, waiting to be read. It is the most scientifically important destination in the solar system that we are not currently sending people to. It is the next great step after Mars, not instead of Mars, but after it. And the case for going there is stronger than most people know. Let us talk about something that never appears in the glossy presentations about Mars colonization, about what the third quarter effect actually means for a multi-year Mars mission, and how the Titan comparison changes that calculation. The third quarter effect is documented across every type of extended, isolated mission: Antarctic winter rovers, submarine deployments, simulated Mars missions, including Mars 500, the 520-day isolation study conducted in Moscow in 2010 to 2011. The pattern is consistent. At roughly 60 to 75% of a mission's duration, psychological state reaches a minimum. Motivation is lowest. Interpersonal friction is highest. Cognitive performance is measurably reduced. For a Mars mission with a total duration of roughly 2.5 to 3 years, the third quarter effect falls somewhere between months 18 and 24. This is after the excitement of arrival has faded, after the routine of operations has become genuinely routine, and when return is still more than a year away. When the crew most needs to perform, doing the complex science and engineering that justifies the mission, their psychological resources are at their lowest point. The primary factors that modulate the severity of the third quarter effect in research, the ability to exit the confined environment, communication quality with the outside world, environmental variety, and perceived meaningfulness of the work. On Mars, exit from the habitat is a radiation event. Every surface excursion is a radiation dose calculation. During global dust storms, it is impossible. The outside environment, when accessible, is the same rocky plain. Communication with Earth has a delay of 3 to 22 minutes each way. Real dialogue is not possible. Environmental variety is geologically interesting, but visually monotonous. On Titan, exit from the habitat is a thermal event. Put on the insulated suit, go outside into 1.5 atmospheres of nitrogen. Radiation is not the limiting factor. During any surface excursion, the environment is organically varied. Different dune fields have different compositions. The approach to the methane seas offers a horizon over open liquid. Weather varies. The methane humidity, the visibility through the orange haze, the gentle surface winds. Communication delay to Earth is 68 to 84 minutes each way. Similar problem to Mars in different magnitudes. The point is not that Titan makes the third quarter effect disappear. Nothing makes it disappear. It is a fundamental feature of human psychology under extended isolation. The point is that some of the environmental factors that modulate it are better on Titan than on Mars. Not all of them, but some. And those some matter for multi-year habitation. Let us now talk about a specific concrete example of how the Titan atmospheric density changes the engineering calculus for something as basic as landing a crewed spacecraft. Landing on Mars is difficult. The atmosphere is thin. Not thin enough to ignore, it creates a significant heating problem during entry, but too thin to effectively brake the spacecraft without additional mechanisms. This is the 7 minutes of terror problem. The entry, descent and landing phase for Mars missions is one of the most technically challenging sequences in spaceflight. The largest payload ever landed on Mars using Mars's atmospheric braking is the Perseverance rover at about 1,025 kilograms. To land humans on Mars, who require life support, food, water, equipment, and a habitat, the landed mass needs to be on the order of 10 to 100 times larger than Perseverance. Current Mars landing systems, parachutes, airbags, sky cranes, do not scale to these masses. New systems are needed. Supersonic retropropulsion, firing engines while still supersonic in the thin Martian atmosphere, is one approach. These systems are being developed. They are not easy.
Landing on Titan is an aerobraking paradise by comparison. The atmosphere is so thick that a spacecraft entering from space is slowed dramatically by aerodynamic forces alone. The Huygens probe, which had no parachutes initially, was braked from 6 kilometers per second to subsonic speeds by the atmosphere alone before its parachutes deployed. For a crewed spacecraft landing on Titan, the thick atmosphere allows much larger parachute and aeroshell systems to function effectively. The delta velocity that must be managed by propulsion is smaller because the atmosphere does more of the braking work. The final approach can be managed by the flight characteristics of the atmospheric region rather than purely by propulsive thrust. This does not mean landing on Titan is trivial. Minus 179 degrees Celsius and a methane weather system create their own challenges. But the fundamental physics of entry, descent and landing on Titan is more favourable for large landed masses than the fundamental physics on Mars. A crewed Mars landing is harder than a crewed Titan landing from a purely atmospheric physics standpoint. This fact is almost never mentioned. Let us now talk about what the specific science of the outer solar system teaches us about the broader question of planetary habitability, and why Titan's position in that picture is uniquely valuable. The concept of a habitable zone, the range of distances from a star where liquid water can exist on a planet's surface, was for decades the primary framework for thinking about where life might exist. Earth is in the Sun's habitable zone, Mars is marginal, Venus is inside it. This framework has been dramatically expanded by our exploration of the outer solar system. Europa is not in the Sun's habitable zone. It is 5 times farther from the Sun than Earth, but it has a liquid water ocean maintained by tidal heating from Jupiter. It is potentially habitable. Enceladus is not in the habitable zone. It is 10 times farther from the Sun, but it has a liquid water ocean with active hydrothermal vents, confirmed by Cassini's direct sampling of its plumes. It is potentially habitable. Titan is not in the habitable zone for liquid water. Its surface water is frozen solid, but it may be habitable by a different chemistry altogether, methane-based life requiring no liquid water at all. Or it may harbour a subsurface water ocean. Or it may be the universe's laboratory for prebiotic chemistry that never quite crossed the threshold to life. In all 3 cases, the concept of habitability has broken free of the classical habitable zone. Life, or the conditions that could support it, may exist throughout the outer solar system. Tidal heating, chemistry, and alternative biochemistry all extend the possible range far beyond what the simple distance from star calculation implies. Titan sits at the centre of this expanded understanding. It tests the hypothesis that complex prebiotic chemistry can exist without liquid water at the surface. It tests the hypothesis that alternative biochemistries are possible. It tests whether life is specific to water-based chemistry or whether the universe offers other solutions. These tests cannot be done at Mars. Mars is a water world, or rather was, and its habitability question is fundamentally about whether ancient water-based life existed or left traces. Mars answers one question.
Titan answers different questions. And the different questions Titan answers may be more fundamental to our understanding of life as a universal phenomenon. Let us now talk about the specific case of Dragonfly's target of the Selk impact crater, and why this single target could produce the most scientifically significant results of any planetary mission in history. Selk crater formed when a large impactor hit Titan's surface. The impact was energetic enough to melt the water ice that makes up a substantial fraction of Titan's icy crust. Modelling suggests that liquid water was present at the crater site for potentially 1,000 to several thousand years after the impact. During those 1,000 years, liquid water was in direct contact with the organic-rich surface material of Titan. The organic material of Titan's surface is extremely chemically rich. Tholins and other photochemically produced compounds, including amino acid precursors and nucleobase precursors. Water plus organic precursors plus time. This is the exact set of conditions that most models of the origin of life on Earth invoke as necessary. Warm little pond chemistry.
Hydrothermal chemistry. All of these share the common feature of water in contact with organic compounds with an energy source. At Selk crater, this experiment ran for thousands of years, and the products have been frozen at -179 Celsius ever since. The cold does not destroy the chemistry, it preserves it. When Dragonfly reaches Selk and DRAMS analyzes the surface material, it will be sampling the results of a water organics chemistry experiment that ran for thousands of years and has been in cold storage for perhaps hundreds of millions of years. If amino acids formed in those 1,000 years of liquid water, they are there, frozen, waiting. If nucleobases formed, they are there. If something more complex formed, polymers, vesicles, any kind of organized molecular assembly that hints at the direction of life, it might be there. If nothing formed beyond the starting materials, that too is information.
That tells us that the specific conditions at Selk, the particular chemistry, temperature, duration, were not sufficient for prebiotic synthesis to proceed to amino acids and nucleobases, which tells us what conditions are necessary. There is no other location in the solar system where this specific experiment has been preserved in this specific way. There is nowhere else we can go and sample the frozen products of a water organics chemistry experiment that ran on a prebiotic timescale. Selk crater is unique. Dragonfly is going there. Let us now talk about something that illustrates the true challenge of the Mars comparison at a human level, about what radiation dose accumulation actually means for the people who live on Mars versus on Titan. The career radiation limit for NASA astronauts is approximately 1,000 millisieverts. This is the total dose an astronaut is permitted to receive across their entire career, set at a level estimated to raise lifetime cancer risk by about 3%. At 250 millisieverts per year, a reasonable Mars surface estimate, a Mars resident hits the NASA career limit in 4 years. After 4 years on Mars, by NASA's current standards, a person has received their lifetime allowable dose and should not receive additional occupational radiation exposure. This is not a death sentence. Cancer risk at 1,000 millisieverts is elevated but not catastrophic, about 3% additional lifetime risk. But it means that the Mars residency, as currently understood, is a 4-year proposition under current occupational health standards. Longer stays require either accepting elevated risk beyond current standards or developing substantially better radiation shielding systems for surface habitats and suits, or revising the standards, which requires extensive epidemiological justification.
At 5 to 6 millisieverts per year, the Titan surface estimate, the NASA career limit is reached after roughly 170 to 200 years. No human lives that long. The radiation limit is not a practical constraint for Titan's surface habitation. This difference transforms what long-term human presence looks like. On Mars, every year of residence is consuming a finite radiation budget. After some years, continued residence requires a conscious decision to accept elevated health risk. For a permanent Martian settlement, radiation exposure is an ongoing health management challenge that compounds over a lifetime. On Titan, the radiation budget is essentially unlimited for human timescales. People can live there indefinitely from a radiation standpoint without accumulating a dose that raises cancer risk to concerning levels. For the second and third generation of any settlement, born there, living their entire lives there, this difference is enormous.
Children growing up on Mars would receive their lifetime radiation dose within a few decades of normal life. Children growing up on Titan would receive doses comparable to those received by their counterparts on Earth. The multi-generational viability of a Titan settlement is substantially greater than that of a Mars settlement from the radiation standpoint alone. Let us now talk about one of the most intriguing specific scientific mysteries that Titan presents, about what the magic island of Ligeia Mare tells us about the dynamic nature of this world. In 2013, Cassini's radar observations of Ligeia Mare, Titan's second largest sea, showed a bright feature that had not been there in previous observations. Subsequent observations showed the feature changing shape, moving, and eventually disappearing. NASA scientists nicknamed it the Magic Island. The specific mechanism behind the Magic Island is still uncertain. Several explanations have been proposed. Waves. Titan's seas are large enough and the atmosphere dense enough that significant wave action is possible under certain wind conditions. Waves on a methane sea would reflect radar differently than flat liquid, creating transient, bright features. Nitrogen bubbles. Liquid methane can dissolve nitrogen gas. If the sea temperature changes, or if a fresh flow of methane enters the sea, dissolved nitrogen could come out of solution as bubbles, creating a fizzing region that reflects radar differently. Like carbonation in a soda bottle. Floating organic material. Organic particles from Titan's surface could be buoyant in liquid methane and ethane under some conditions and not others, depending on temperature and composition. A floating mat of organics that appears and disappears as conditions change would produce a magic island appearance. All of these explanations require that Titan's seas are actively dynamic systems, not static liquid bodies, living hydrocarbon seas with currents, chemistry, temperature gradients, and material exchange with the atmosphere and the solid surface. For a future human presence near the Titanian seas, this dynamism matters. The seas are not dead pools of liquid, they are active chemical systems. Understanding their dynamics, which Dragonfly's atmospheric and chemical measurements will contribute to, and which a future sea surface mission could directly investigate, is prerequisite to understanding whether they harbour chemistry or biology. The Magic Island is a reminder that Titan surprises us, that this world, despite 13 years of Cassini observation, still has things we have not seen or understood. The surface is not fully mapped at high resolution. The sea chemistry is sampled only spectroscopically from orbit. The interior is not directly probed. There is a tremendous amount of Titan left to discover. Let us now talk about the specific engineering concept that makes a long-duration Titan mission potentially more sustainable than an equivalent Mars mission, about the ISRU, In Situ Resource Utilization calculus for each world. ISRU, using local resources rather than carrying everything from Earth, is the key to any truly long-term off-world presence. The cost of transporting mass from Earth to another planet is so high that any mass that can be sourced locally rather than transported represents an enormous practical advantage. On Mars, ISRU is the subject of significant current research. The MOXIE instrument on Perseverance demonstrated oxygen production from atmospheric CO2, a proof of concept that Mars's CO2 atmosphere can yield breathable oxygen with the right electrochemical process. Water extraction from subsurface ice is feasible in principle. Nitrogen for plant growth is present in the atmosphere at low partial pressure. What Mars ISRU cannot easily provide: nitrogen at useful partial pressures. The total nitrogen available per cubic meter of Mars' atmosphere is very low. Hydrogen for fuel, sparse on Mars. Complex organic compounds for materials and agriculture, degraded by UV and perchlorates on the Martian surface. On Titan, ISRU offers a different profile. Nitrogen is the main constituent of the atmosphere at 1.5 atmospheres. It is abundant at any scale. Water is available as ice and can be melted for drinking, agriculture, and electrolysis to oxygen. Methane and ethane from the atmosphere and surface lakes are available as chemical feedstocks or fuel, with imported or electrolytically produced oxygen as oxidizer. Complex organic chemistry, tholins and other photoproducts, is available on the surface in vast quantities. What Titan ISRU cannot easily provide: silicon and metals for construction and electronics. The surface chemistry is predominantly organic and icy. Silicate rocks exist, but are buried under organic layers. Solar energy, essentially zero utility. The comparison: Mars offers somewhat more accessible mineralogy, but severely limited nitrogen and organics. Titan offers abundant nitrogen and organics, but requires nuclear energy for all processes and has more challenging solid material extraction. For a settlement whose primary needs are food, oxygen, nitrogen, water, and basic materials, Titan's ISRU profile is arguably better than Mars's beyond the short term. The nitrogen alone, necessary for agriculture, for habitat-atmosphere composition, for chemical processes, is a resource Mars cannot provide from its atmosphere at useful rates. Titan provides it free, at ambient pressure, in enormous quantities. Let us now talk about something that is both concrete and profound, about what the choice of Titan as a destination tells us about the kind of questions we care about as a civilization. Every major exploration program in history has been shaped by the questions the civilizations sending the explorers cared about most. The great European voyages of the 15th and 16th centuries were shaped by the question, where can we trade profitably and where can we claim territory and resources? The answers were America, the Spice Islands, the coasts of Africa. The 19th century Arctic and Antarctic expeditions were shaped by the question, what is at the geographic extremes of our planet and can we get there first? The answers were the poles, mapped and claimed at enormous human cost. The Apollo program was shaped by the question, can we beat the Soviets to the moon? The answer was yes, definitively, in 1969. The Mars program, as currently constituted, is shaped by several questions simultaneously. Can we find evidence of past life on Mars? Can we demonstrate the ability to maintain human life on another planet? Can we build the technical foundation for eventual human expansion? These are good questions. They are not the only questions. The Titan program asks, is life a rare cosmic accident, or is it a near inevitable consequence of chemistry given appropriate conditions? Does life require water specifically, or does it require chemical complexity in any liquid medium? What does prebiotic chemistry look like, preserved over billions of years, in a nitrogen-rich world with organic surface chemistry and a methane hydrological cycle? These questions are about the nature of life at the most fundamental level. They are not questions about what happened on Mars 4 billion years ago. They are questions about the universal principles that determine whether a universe is full of life or almost empty of it? The answer to those questions, whatever they are, will be the most important knowledge the human species has ever acquired about its place in the cosmos. That knowledge is on Titan. And that is the real reason, beyond the atmospheric pressure, beyond the radiation doses, beyond the organic chemistry, that Titan matters. Not just as a next destination, as the place where we find out if we are typical or exceptional, if life is everywhere or almost nowhere, if the universe is, at its core, a place that makes life, or a place that makes our existence the most improbable event in a cold and empty history. The answer is somewhere in that orange haze, and it is worth going there to find it. Let us talk about something that makes the Titan conversation concrete in a way that abstract comparisons do not, about the specific human experience of the first days on each world, reconstructed from what we know. First day on Mars. The crew lands after 6 to 9 months of transit. The habitat is established. The first surface excursion is scheduled. You put on the pressure suit. It takes about an hour with assistance from a crewmate. The suit must be carefully donned, checked, pressurized, verified. The suit inflates to 0.3 atmospheres internal pressure against the 0.006 atmospheres outside. You feel the suit stiffening around you. Moving your arms requires active effort against the suit's pressure. Closing your hands around a tool handle is fatiguing in a way that has no earthly equivalent, except perhaps squeezing a very stiff stress ball for hours. You exit through the airlock. The Martian surface is before you. Red-orange rock and dust in every direction. The sky is a pale brownish orange. The sun a disk noticeably smaller than on Earth. The light slightly different in color temperature from what your evolutionary biology prepared you for. You are thinking about radiation. Not consciously perhaps, but it is there. The knowledge that every minute outside is adding to a cumulative dose that has a finite career limit. There is no immediate sensation. You feel nothing, but you know. The suit's air supply is good for several hours. You begin your surface work. Every tool manipulation requires concentration because the suit resists your hands. After 2 hours, you are physically tired in a way that goes beyond the work you have done. The suit has been working against you the entire time. You return to the airlock, depressurization, donning removal sequence. You are inside again, in the familiar pressurized habitat air. You have been on the surface of Mars. First day on Titan. The crew has landed after a longer transit, 3 to 4 years with nuclear propulsion, or 6 to 7 with chemical. The habitat is established. You put on the thermal suit. It is more like donning a very good expedition suit than putting on a spacecraft. The suit's job is thermal, keeping you at survivable temperature against -179 Celsius outside, and respiratory, providing oxygen from your tank because the outside atmosphere has none. It does not need to be inflated against vacuum. The 1.5 atmospheres outside is actually pressing slightly inward against the suit's outer shell. The suit is flexible. You can close your hands naturally. You can move your arms without fighting suit pressure. You exit through the airlock. The Titan surface is before you. The sky is orange, not the thin brownish orange of Mars, but a rich, deep orange, textured with haze layers that vary with altitude. Visibility is limited, not to a few kilometers as on Mars, but to a few hundred meters, the haze creating a soft edge on everything beyond that distance. The sun is a blurry, bright patch in the orange overhead, not a disk, more like a bright window in a foggy sky. The surface around you is dark brown organic material. The texture is closer to soil than to rock. The tholins and organic sediment have a granular quality.
Rounded ice pebbles protrude from it in places, evidence of past fluid transport. The air around you, which you cannot breathe, is 1.5 atmospheres of nitrogen. It presses gently against you like the beginning of a light wind. This is not a problem. It is, in a strange way, comforting. The presence of atmosphere at all, even the wrong one, is different from the almost vacuum of Mars. You are not thinking about radiation. There is essentially no surface radiation to worry about. The 1.5 atmospheres of nitrogen above you has handled that. You are thinking about the cold, but the suit is handling that. Your thermal readout shows the interior of the suit is at plus 18 Celsius, while minus 179 is outside. The gradient is enormous, but the engineering is managing it. You begin to walk. At 0.14 g, you are lighter than on Titan. Each step propels you higher than expected, the motion more like slow-motion walking than Earth walking. You adapt within minutes. The suit moves with you. In the middle distance, perhaps 200 meters away, there is a dark ridge of organic dune material. To your left, the terrain drops away toward a darker region, possibly a dry riverbed, evidence of past methane flow. You pick up a surface sample. The material comes away easily. It is soft, like damp organic soil. You place it in the collection container. You have been on the surface of Titan. These are not equivalent experiences. They are not even in the same category of experience. One is a spacecraft operation. The other is something closer to a polar field expedition. Both are extraordinary. Both represent milestones in human history. But the daily lived experience of long-term residence, the ergonomics, the radiation psychology, the environmental richness, these are profoundly different. Let us now talk about something that is almost never addressed in discussions of outer solar system exploration, about what it means to build a civilization rather than an outpost, and how Titan's properties change that calculus at generational timescales. An outpost is a place where people go temporarily for specific purposes and return from. A civilization is a place where people are born, live, and die, where there is continuity of culture, society, and community across generations. Most discussion of Mars colonization is implicitly about outposts that become settlements that might eventually become civilizations. The path is long and the endpoint uncertain.
Many serious analysts doubt that a self-sustaining Martian civilization is achievable within any near-term time frame. The challenges at the civilization scale are specific. Children born on Mars receive the same radiation dose as their parents, approximately 250 millisieverts per year. By age 20, a Mars-born child has received 5,000 millisieverts. By age 40, 10,000 millisieverts. These are doses associated with significantly elevated lifetime cancer risk, substantially more than the career limits set for adult professionals who chose to accept that risk. Raising children on Mars is raising them in a radiation environment that we would not consider acceptable for children on Earth. This is a fundamental ethical challenge for any permanent Martian civilization. It is not resolved by habitat shielding alone. Underground habitats can reduce surface dose, but cannot eliminate it entirely, and children who never go outside live in a different kind of environmental deprivation. Children born on Titan receive approximately 5 to 6 millisieverts per year from ambient radiation, comparable to children in regions of Earth with elevated natural background radiation, well within the range of normal variation for humans on Earth. Over a lifetime of 80 years, a Titan-born person would receive about 400 to 480 millisieverts total from ambient radiation. This is below the career limit for occupational radiation workers,
The ethics of raising children on Titan does not include accepting elevated cancer risk from ambient radiation. The ethics of raising children on Mars does. This is not the only consideration for a potential Titan civilization. The cold, the need for nuclear energy, the non-breathable atmosphere all present their own challenges. But from the radiation standpoint, the most biological constraint on multi-generational habitation, Titan is simply not in the same category as Mars. A multi-generational human presence on Titan is ethically more straightforward than on Mars. This matters if the goal is civilization rather than outpost. Let us now talk about the specific technology that matters most for making Titan accessible, about nuclear propulsion and where it stands today. The nuclear thermal rocket works by heating propellant, typically liquid hydrogen, using a nuclear reactor rather than chemical combustion. The propellant is heated to higher temperatures than chemical combustion allows, producing higher exhaust velocities, which means the rocket is more fuel efficient. The specific impulse of a nuclear thermal rocket is approximately 800 to 1000 seconds, compared to about 450 seconds for the best chemical rockets, the Space Shuttle main engine. This improvement in specific impulse, roughly a factor of 2, substantially changes the mass ratio requirements for a given mission.
For outer solar system missions, where the delta velocity required is large, reaching Saturn requires about 10 kilometers per second of delta velocity using optimized trajectories, the improvement in specific impulse reduces the propellant mass needed, which reduces the total launch mass, which reduces cost and enables larger payloads. The effect on transit time is more complex. Higher specific impulse allows a spacecraft to carry the same delta velocity with less propellant, but this does not automatically translate to faster transit. To go faster, you need to apply more delta velocity, which still requires propellant, even with a more efficient engine. However, nuclear thermal propulsion enables trajectory options that are not practical with chemical propulsion. Direct trajectories to Saturn, without the circuitous gravity assist routes that add years to the journey, become more feasible.
A nuclear thermal mission to Titan might take 2 to 3 years rather than 6 to 7 years, depending on the specific trajectory and propulsion parameters. The Draco program, NASA's demonstration rocket for agile cislunar operations, is the current US program to develop and test nuclear thermal propulsion. Draco aims to demonstrate the technology in space by 2027. This is a cislunar demonstration, proving the engine works in space conditions rather than proving it for a specific deep space mission. But the step from demonstration to operational system is incremental. If Draco succeeds, the path from demonstration to an operational nuclear thermal upper stage for deep space missions is approximately 10 to 15 years of additional development. This means nuclear thermal propulsion for outer solar system missions could be available by the late 2030s to early 2040s.
Which means that a crewed mission to Titan using nuclear thermal propulsion, with a transit time of 2 to 3 years rather than 6 to 7, is a plausible mid-century objective rather than a late-century one. The calculus changes substantially when the transit time drops from 6 years to 2 to 3 years. 6 years one way is at the extreme edge of what human physiology and psychology can tolerate in current habitats. 2 to 3 years one way is within the range that Mars transit research is already addressing. Technology makes Titan more accessible, and that technology is in active development right now. Let us now talk about the specific economic argument about what a Titan mission costs compared to what it produces, and why the comparison with Mars programs is not as unfavorable as it might appear.
Cassini-Huygens, which gave us 13 years of Saturn system science, including the basic characterization of Titan that motivated Dragonfly, cost approximately $3.26 billion over its lifetime. Per year of science return, this is approximately $250 million per year for extraordinary scientific discovery, including the confirmation of Titan's methane seas, the discovery of Enceladus's plumes, and the foundational data that enabled the Dragonfly mission. Dragonfly costs approximately $3.35 billion for a 2.7-year primary mission, roughly $1.2 billion per year of surface science. This is more expensive per year than Cassini, but returns ground truth data from the surface that orbital data simply cannot provide. For comparison, the Mars 2020 mission, including Perseverance, costs approximately $2.7 billion. The Mars Science Laboratory, including Curiosity, cost approximately $2.5 billion. These are comparable to Dragonfly in cost scale.
The scientific return from Dragonfly, if DRAMS detects amino acids or nuclear bases at Selk crater, is potentially the most significant discovery in the history of science. The probability of that specific discovery is uncertain, but the scientific community considered it high enough to select Dragonfly over several competing mission proposals. The cost per unit of potentially paradigm-shifting discovery at Titan is arguably lower than almost anywhere else we could send a spacecraft. Not because Titan is cheap to reach, it is not, but because the specific scientific questions that Titan can answer are uniquely fundamental. You cannot buy the answer to "Is life a universal phenomenon or a singular accident?" by sending $1 billion to Mars. You might be able to buy an approximation of it by sending $3 billion to Titan. That is not a bad investment. Let us now talk about what the global scientific community's view of Titan actually is, beyond NASA's specific program decisions, because the breadth of international interest in Titan is itself evidence of its scientific priority. The Decadal Survey, the US National Academy's ranking of scientific priorities for planetary science, published every 10 years, ranked a Titan exploration mission as a high priority in both the 2013 to 2022 and 2023 to 2032 surveys. Dragonfly is a direct result of this prioritization. But international interest is broader. JAXA, the Japan Aerospace Exploration Agency, has expressed interest in Titan science as part of its Outer Solar System program. ESA, the European Space Agency, contributed Huygens to the Cassini-Huygens mission and has studied Titan missions independently. The scientific community studying Titan spans dozens of countries. Cassini's science team included researchers from the US, Europe, and beyond. The papers being published today analysing Cassini data come from scientists worldwide. This breadth of interest is not coincidental. Titan is not a priority because one country has an interest in it. It is a priority because the scientific questions it addresses, origin of life chemistry, alternative biochemistry, prebiotic organic chemistry, are questions that the entire astrobiology community has identified as fundamental. When the global scientific community, with the broadest possible range of perspectives and expertise, consistently ranks a destination as high priority, this is meaningful evidence. It is not marketing or advocacy. It is the collective judgment of the people who understand these questions best. Titan is their answer to the question of what matters most. Let us now talk about something that is both practically important and philosophically resonant, about what the presence of rain means for human psychology at the deepest level. Rain is one of the oldest sensory experiences of human existence. Our ancestors evolved in a world with rain. The smell of rain on soil, petrichor, is produced by geosmin, a compound released by soil bacteria, detected by humans at concentrations of 5 parts per trillion. We evolved to detect rain smell with extraordinary sensitivity because our survival depended on knowing when rain was coming. Rain on a shelter, rain on leaves, the sound of rain, the visual change in the atmosphere before rain. All of these are deep in our evolutionary heritage, linked to survival, to agriculture, to the seasonal patterns that structured human life for hundreds of thousands of years. No weather on Mars resembles rain in any way that engages this heritage. The dust storms are hostile events to shelter from. The frost that forms on the surface at certain seasons is geologically interesting, but not emotionally resonant. The thin atmosphere produces no sound that a human ear would register as weather. On Titan, it rains. Not water rain, not rain that smells like petrichor, not rain that makes the sound that rain makes on an earth roof, but it is rain, liquid falling from clouds in drops, striking the surface and running off, collecting in rivers, rain that has carved channels and valleys and shaped a landscape over billions of years, in the same way that water rain has shaped Earth. For a person living on Titan, hearing the sound of methane rain on the habitat exterior through sensors converted to audio, watching on cameras as the organic dunes darken with fresh liquid, knowing that rivers are flowing somewhere in the haze, this is weather, real weather, dynamic atmospheric chemistry expressing itself at the human scale. The psychological difference between living in a dead world that never has weather and living in a world that rains, even methane rain in an atmosphere you cannot breathe, is not trivial. It is the difference between geological time and meteorological time, between a world that exists on scales that make human experience feel irrelevant, and a world that has a daily and seasonal rhythm that connects, however imperfectly, to something in our evolved sensory heritage. This matters for the long-term psychology of habitation in ways that are real, even if they are difficult to quantify. Rain on Titan, falling now, while you read this, while the sun is a blurry patch in an orange sky and the methane seas at the North Pole are rippling in a distant wind. It is raining on Titan right now, and that is not nothing. Let us talk about something that connects the scientific case for Titan to the cultural case, about how the first images from Dragonfly will change the public imagination in the same way that specific images have changed it before. There are images in the history of space exploration that did not merely document, they transformed. The Earthrise photograph, taken by Apollo 8 astronaut William Anders on December 24, 1968, Earth rising over the lunar horizon, brilliant blue and white against the black of space, is credited with catalyzing the environmental movement. It gave humanity a view of itself from outside itself for the first time. You could count the specific policy changes that followed, the organizations founded, the treaties signed, the legislation passed that drew inspiration from the emotional impact of that single image. The pale blue dot, Earth as a tiny speck of light in a sunbeam, photographed by Voyager 1 in 1990 at Carl Sagan's request from 6 billion kilometers away, became one of the most widely quoted scientific images in history. Sagan's words, written in response to it, have been read by millions. The image itself appears in countless contexts as shorthand for perspective, humility, and the smallness of human concerns against cosmic scale. The first images from Mars surface landers, Viking in 1976, Pathfinder in 1997, Spirit and Opportunity in 2004, Curiosity in 2012, Perseverance in 2021, each produced a moment of collective attention. People stopped what they were doing to look at a photograph of a rock field on another planet. Because it was another planet. Because humans made something that got there and could send back a picture. The images themselves were, individually, images of rocks, but the context made them transformative. The first images from Dragonfly Taken from a rotorcraft hovering a few meters above the surface of Titan, looking out at orange dunes under an orange sky with the distant smear of the sun, will be different from any previous image in the history of planetary exploration. Not rocks, dunes made of organic chemistry. Not a thin pinkish sky, a thick orange atmospheric column visible to the horizon. Not the same visual vocabulary as every Mars image ever taken. A new visual vocabulary for a new kind of world. And if Dragonfly is near the methane seas, if a version of the mission reaches the shores of Ligeia Mare or the Kraken Mare, the first image of a liquid surface on a world other than Earth will be taken. Not implied by radar data, not inferred from chemistry, directly imaged, a shoreline, a horizon over open liquid, perhaps waves. The cultural impact of that image will be comparable to Earthrise, not because scientists predicted it would be,
because the human response to seeing a sea on another world at a comprehensible scale from the perspective of something standing at its shore will be viscerally different from seeing a graph of radar reflectivity. The mission to Titan is also a mission to produce images that change minds. Images that make Titan real in the way that only visual experience can make something real for a species that evolved with vision as its primary sense. Those images do not exist yet. In 2034, they will. Let us now talk about the specific atmospheric chemistry of Titan that makes it a unique natural laboratory, about the tholins and what decades of laboratory research have revealed about what they actually contain. Tholins are the complex organic polymers produced when nitrogen and carbon-containing gases are irradiated by UV light or energetic particles.
The word was coined by Carl Sagan and his collaborator Bishon Kare in 1979, from the Greek word for muddy, because tholins are typically dark brown to reddish brown. In laboratory experiments simulating Titan's atmospheric conditions, a gas mixture of nitrogen and methane irradiated by UV light or electrical discharge, the resulting tholins contain amino acids, multiple amino acids, including glycine, alanine, and others that are found in proteins. Not identical in distribution to the amino acids preferentially used by Earth life, but the same molecules. The building blocks of proteins formed spontaneously under conditions approximating Titan's atmosphere. Nucleobases, the molecular components of DNA and RNA, adenine, guanine, cytosine, uracil, have been detected in laboratory tholins. The information-carrying molecules of Earth life form spontaneously under Titan atmospheric conditions. Urea, one of the first organic molecules ever synthesized in a laboratory, Friedrich Wöhler's synthesis of urea from ammonium cyanate in 1828 was a landmark in chemistry, is present in Titan tholins. Complex polymer chains, long carbon-nitrogen chains that do not have direct biological analogues, but that represent the kind of complexity that might be a precursor to more organized molecular systems. This is not speculation. These detections were made in earthly laboratories using Titan atmospheric simulation chambers. The chemistry is established. Amino acids form in Titan atmospheric conditions. The question is, what happens to these amino acids over billions of years on the actual surface of Titan? Laboratory simulations show what happens over minutes to hours. Titan's surface has been processing this chemistry for roughly 4 billion years. 4 billion years of amino acid production settling onto a surface and undergoing further reactions. 4 billion years, during which, at Selk Crater and other impact sites, liquid water was periodically added to the mixture. 4 billion years, during which whatever life emerged from this chemistry, if anything emerged, had time to evolve. The result of this 4 billion year experiment is preserved right now in the frozen organic coating of Titan's surface. We have a mass spectrometer capable of reading it, launching in 2028. Let us now talk about what the discovery of amino acids at Selk Crater would actually mean, concretely, scientifically, for the interpretation of life's origins and distribution. Amino acids have been found in meteorites. The Murchison meteorite, a carbonaceous chondrite that fell in Australia in 1969, contains dozens of amino acids, including several not found in terrestrial biology. This demonstrates that amino acids form in space environments through abiotic chemistry. They are not uniquely biological. So finding amino acids on Titan does not prove life. Amino acid detection alone is expected. Laboratory simulations have already shown they should be there. What Dragonfly adds is the ability to detect chiral signatures. In biological systems, all amino acids used by Earth life are left-handed, L form. All sugars are right-handed, D form. This homochirality, using only one mirror image form of each molecule, is a property of living systems that abiotic chemistry does not produce. Abiotic chemistry produces roughly equal left and right forms, a racemic mixture. If DRAMS finds amino acids at Selk Crater in a racemic mixture, this is consistent with abiotic chemistry. Expected result: interesting but not transformative. If DRAMS finds amino acids at Selk Crater with a significant enantiomeric excess, more of one form than the other, this is the signature of biological processing. Either Earth-like life using the same biochemical handedness we use, or a different life using the opposite handedness. Either way, biology. The chiral measurement at Selk is therefore the critical test. It is what separates interesting prebiotic chemistry from evidence of life. DRAMS is designed to make this measurement. It has the sensitivity to detect enantiomeric excess at biologically relevant levels if it is present. If the measurement shows enantiomeric excess, the scientific response will be overwhelming. Every available space agency resource will be directed toward confirmation. A follow-on mission will be prioritized above everything else. Human missions to Titan will become an urgent scientific and political priority. If the measurement shows racemic, this is still enormously valuable. It characterizes what 4 billion years of Titan prebiotic chemistry produces without biological intervention. It tells us what step life must take beyond racemic amino acid chemistry, and where that step might have occurred or failed to occur. Either result is worth $3.35 billion and 6 years of transit time. Let us now talk about the specific way that Titan fits into the broader search for life in the universe, about how it changes the probability estimates for life beyond Earth, regardless of what Dragonfly finds. The Drake equation, Frank Drake's framework for estimating the number of active communicating civilizations in the galaxy, contains a term typically written as FL, the fraction of habitable planets on which life actually emerges. This fraction is the most uncertain term in the equation. We have exactly one data point, Earth, and Earth provides a lower bound of 1. Life definitely emerged on Earth, but tells us nothing about whether this was easy or extraordinarily improbable. Current estimates of FL vary by many orders of magnitude. Some researchers argue floor approaches 1, that wherever conditions are right, life emerges. Others argue it might be 10 to the minus 20 or smaller, that the origin of life is so improbable that Earth may be the only example in the observable universe. Finding life on Titan, if it happened, would be the most powerful possible data point for high floor. 2 independent origins of life within one solar system implies that life emerges easily whenever conditions allow. If floor is high, the universe is full of life. Finding advanced prebiotic chemistry on Titan, but no life, would be informative about where the bottleneck is, what step life failed to take, and would suggest floor is lower than the optimistic estimates. Finding only basic chemistry, amino acids in racemic distribution, no complexity beyond what laboratory simulations predict, would suggest that the specific conditions needed for life to emerge are harder to meet than Titan provides. This would imply floor is lower still.
Each of these outcomes moves the needle on the most important unknown in the search for life, not by giving us another star's data, but by doubling, or failing to double, our data points within our own solar system. One additional example of life is worth more than any amount of radio search at this stage of our understanding, and Titan is the most plausible place in the solar system where that additional example might exist. Let us now talk about the specific concept of Titan as the solar system's organic chemistry museum, about why its preservation of complex chemistry is unique and what it enables. The timeline of organic chemistry in the solar system, early solar system, the first few 100 million years after formation, intense bombardment, organic molecules present in meteorites and comets, warm planetary surfaces where chemistry could occur in liquid water or ice. This is the era of origin of life on Earth. Life appears in the geological record by 3.7 to 3.8 billion years ago, within a few 100 million years of Earth's formation. Earth today, all prebiotic chemistry has been overwritten. The geological record from 4 billion years ago is almost entirely absent. The chemistry that preceded life, that produced the first self-replicating molecules, is gone, consumed, cycled through 4 billion years of biological, geological, and chemical processing. We cannot directly study what happened. Mars, some preservation of early chemistry in ancient rocks. But the surface was sterilized by UV after the magnetic field was lost 4 billion years ago. The oxidizing perchlorates destroy organic compounds. Whatever was preserved has been heavily modified by billions of years of UV radiation and oxidizing chemistry. Titan, a different story. Titan's atmosphere has been continuously producing complex organic chemistry for billions of years. The cold temperatures preserve what is produced. The thick atmosphere shields the surface from destructive UV. The surface is an accumulation of atmospheric chemistry going back essentially to Titan's formation. Titan is the solar system's archive of organic chemistry. Not a perfect archive. It records what Titan's specific atmospheric processes produce, not exactly what happened on early Earth. But it is a far better preservation environment than anywhere else accessible. When geologists want to understand ancient Earth history, they look for the oldest, least altered rocks they can find. Rocks that preserve information before it was overwritten by later processes. The Eoarchean rocks of the Acasta Gneiss complex in Canada, dated to 4.02 billion years ago, are treasured precisely because they preserve information about early Earth conditions. Titan's surface is the astrobiology equivalent of the Acasta Gneiss, a preserved record of conditions and chemistry that no longer exist in the same form anywhere more accessible. Reading it tells us about the universe at a stage we cannot observe directly on Earth. Let us now talk about something that is both practically important and philosophically satisfying, about why the case for Titan is not in opposition to the case for Mars, but is made stronger by it. Mars exploration will develop technologies that Titan exploration needs. Life support systems capable of sustaining humans for years in isolation and confinement, developed for Mars, will be adapted for Titan. Nuclear power systems for Mars habitats, developed because solar power is insufficient at Mars distances, will be further developed for Titan, where solar power is even less viable. Psychological protocols for long-duration isolated missions, developed from Mars transit and surface experience, will be refined for Titan. The investment in Mars is not investment that could have gone to Titan. It is investment that builds the foundation for Titan.
Similarly, the scientific knowledge from Mars shapes the Titan research agenda. Understanding what prebiotic chemistry on a rocky planet with past water looks like tells us what to compare Titan's organic chemistry against. The astrobiology developed to guide Mars sample return, what biosignatures to look for, how to avoid false positives, how to interpret ambiguous results, is directly applicable to Dragonfly's analysis of Titan's surface chemistry. Mars and Titan are not competitors in a zero-sum resource game. They are sequential chapters in a single program. Humanity learning to understand and occupy the solar system beyond Earth. The argument for Titan is not instead of Mars, it is after Mars. And the point of making the argument now, before Mars programs are fully underway, is to ensure that Titan is the destination that follows. Not Ceres, not Vesta, not Europa, as extraordinarily scientifically important as Europa is. Titan. Because Titan is where the organic chemistry is, where the weather is, where the atmosphere is, where the radiation is manageable, where flight is natural, where the scientific questions about life's universality can be directly addressed. Titan is the right next step after Mars. And making that case now, in the 2020s, while the decisions about the 2040s and 2050s are being made in budget offices and scientific committees and space agency planning documents, is what ensures that Titan gets the investment it needs to become the destination it should be. The orange haze is waiting. The methane rain is falling right now. Dragonfly is being built. And the most important question in science, are we alone, or is life what the universe does when the chemistry is right, is sitting frozen on the surface of a moon of Saturn, waiting to be read. Let us talk about something that is rarely discussed in the context of Titan exploration, about what the presence of a thick atmosphere means for the long-term process of terraforming, and why this makes Titan's long-term potential fundamentally different from Mars's. Terraforming, the process of modifying a planet's environment to make it habitable for Earth life without protective equipment, is an idea that has been seriously explored for both Mars and Titan. The Mars terraforming problem is immense. Mars has lost most of its atmosphere. To give Mars a breathable atmosphere would require importing or releasing enormous quantities of nitrogen and oxygen. The estimates for nitrogen alone, making up 78% of Earth's atmosphere, require releasing more than 10 to the power of 18 kilograms of nitrogen into the Martian atmosphere. There is not enough nitrogen accessible on Mars to do this. Importing it from elsewhere in the solar system would require moving mass at scales that strain even the most optimistic long-term technology projections. Maintaining a terraformed Mars atmosphere against the solar wind, without a global magnetic field, would require continuous replenishment. Carl Sagan proposed the idea of terraforming Mars in the 1970s. Serious analysis in subsequent decades has made most planetary scientists more skeptical, not less. The nitrogen problem alone may be insolvable within any practical human timescale. The Titan problem is different and in some ways easier. Titan's atmosphere already exists. It is already thick, 1.5 atmospheres. It is already mostly nitrogen, the primary component of Earth's atmosphere.
What it lacks for breathability is oxygen, and oxygen on Titan is available in the form of water ice that can be electrolyzed. The challenge is not building an atmosphere from scratch. The challenge is enriching an existing atmosphere, adding oxygen to a nitrogen base that already exists in the right quantity. Christopher McKay and others have proposed a Titan warming and oxygenation strategy. Titan's surface temperature is maintained in part by the anti-greenhouse effect of its haze layer. the haze reflects some of the faint solar light back to space. If the haze could be reduced by destroying the photochemical precursors or by adding specific catalysts, Titan's surface would warm. At somewhat warmer temperatures, the methane seas might partially evaporate, adding methane to the atmosphere. The chemistry changes.
McKay's analysis suggests that with sufficient warming, using orbital mirrors to concentrate sunlight, or by breaking down the nitrogen-methane atmosphere in ways that release other gases, Titan's surface might eventually reach temperatures where liquid water is possible. At that point, biological processes could produce oxygen. Over thousands or millions of years, a breathable oxygen atmosphere might develop. This is speculative, very long-term, requires technologies we do not have, and raises profound ethical questions about whether we should terraform at all, particularly if Titan has indigenous life that we would be destroying. But the point is structural. Titan's terraforming problem has a path that does not require building an atmosphere from scratch. It requires modifying an existing atmosphere that is already mostly the right composition and already at the right pressure. Mars's terraforming problem requires building an atmosphere from materials that are not in sufficient quantity anywhere accessible. In the very long-term vision of human expansion through the solar system, Titan's starting conditions are more favorable for eventual transformation than Mars's. Let us now talk about the specific way that Titan's methane cycle parallels Earth's water cycle, and why this parallel is more than metaphorical. Earth's water cycle. Water evaporates from the ocean surface driven by solar heating. Water vapor rises in the atmosphere and cools. Cooling causes condensation, cloud formation. Clouds produce precipitation, rain and snow. Precipitation falls on land, runs off in rivers and streams, collects in lakes, flows back to the ocean. The cycle repeats, redistributing fresh water globally, shaping topography through erosion and sustaining the biosphere.
Titan's methane cycle. Methane evaporates from the surface of the northern seas, driven by the slightly warmer conditions of Titan's northern summer. Methane vapor rises in the atmosphere and cools. Cooling causes condensation, methane cloud formation. Methane clouds produce precipitation, methane rain. Methane rain falls on the surface, runs off in methane rivers, collects in lakes and seas. The cycle repeats. The structural parallel is essentially complete. Different working fluid, methane instead of water. Different temperatures, -179 instead of +15. Different geographic distribution, most liquid confined to polar regions rather than the global distribution of Earth's oceans, but the same basic cycle. This cycle shapes Titan's topography through the same erosional processes that water shapes Earth's topography.
The river channels visible in Cassini radar imagery were not carved by volcanic processes or tectonic processes. They were carved by flowing methane, eroding the water ice bedrock of Titan's surface over geological time. The rounded pebbles that Huygens photographed at its landing site, water ice pebbles rounded by tumbling in methane rivers or lake waves, are direct evidence of the erosional power of Titan's methane cycle. For a human presence on Titan, this cycle is more than scenically interesting. It represents a predictable, regular, seasonal redistribution of liquid across the surface. Methane rain season means fresh liquid available at previously dry locations. Dry season means different surface conditions. The cycle drives the geology, drives the organic chemistry redistribution, drives the surface dynamics. Understanding this cycle, which Dragonfly's meteorological instruments will contribute to, and which extended mission scenarios near the seas will directly observe, is prerequisite to understanding where to site a long-term habitat, how to access liquid resources, and how to plan operations across Titan's 7.5-year seasons. A human civilization on Titan lives inside this cycle, in the same way that Earth civilizations live inside Earth's water cycle. It is the dominant environmental rhythm of the world. Let us now talk about the specific scientific case that has recently been strengthened by new theoretical work, about the possibility of a subsurface liquid water ocean on Titan. Cassini's radio science experiment, measuring how Titan's gravity field changed as the spacecraft flew over different regions, provided evidence for a global subsurface ocean of liquid water, possibly mixed with ammonia, beneath Titan's icy shell. The evidence: Titan's surface appears to flex more than expected under the tidal forces of Saturn, the same tidal heating mechanism that keeps Europa's ocean liquid. The amount of tidal flexing implies that the interior is not entirely solid, that there is a liquid layer somewhere between the icy crust and the rocky interior. The most straightforward interpretation is a global liquid water ocean beneath the ice shell, perhaps 50 to 100 kilometers below the surface. This ocean, if it exists, would be maintained by tidal heating from Saturn and potentially by radiogenic heat from the rocky core. The ammonia content is important. Ammonia is an antifreeze that dramatically lowers the melting point of water-ammonia mixtures. A mixture of water with roughly 30% ammonia remains liquid at temperatures that would freeze pure water solid. This allows a subsurface ocean to exist on Titan despite the extreme surface cold. If this subsurface ocean is real, Titan joins Europa and Enceladus as worlds with potentially habitable liquid water environments beneath their surfaces. Titan would have not one, but potentially two environments with conditions that might support life: the methane surface chemistry and the subsurface water ocean. Dragonfly's seismometer, designed to detect internal structure through seismic signals, will contribute to constraining the existence and properties of this ocean. So will its magnetometer. The combination of surface chemistry measurements and geophysical measurements may tell us whether material from a subsurface ocean is reaching the surface through cryptovolcanic activity, and whether that material contains chemistry relevant to life. The possibility of a subsurface water ocean transforms Titan from a prebiotic chemistry lab into something more. It makes Titan potentially analogous to Europa, but with the extraordinary surface organic chemistry that Europa lacks. If both environments, surface and subsurface, contribute to each other's chemistry through cryptovolcanism that brings subsurface water to the surface, and through eventual reburial of surface organics, then Titan is not just two separate potentially habitable environments. It is an integrated system where prebiotic chemistry produced at the surface might interact with water-based chemistry from the interior. This is a uniquely complex and uniquely interesting astrobiological scenario. Nothing else in the solar system quite matches it. Let us now talk about the specific way that the nitrogen in Titan's atmosphere connects to one of the most important unsolved problems in the origin of life, about the synthesis of nitrogenous bases. The bases of DNA and RNA, adenine, guanine, cytosine, thymine, uracil, are nitrogen-containing aromatic ring structures. Their synthesis under prebiotic conditions on Earth is one of the key unsolved problems in origin of life research. While these bases have been detected in meteorites and can be produced in laboratory simulations, the specific pathways and conditions that produce them efficiently enough to be relevant for life's origin are actively researched. One of the most studied pathways involves hydrogen cyanide, HCN, as a precursor. Adenine, for instance, can be produced by the polymerization of 5 HCN molecules. HCN is present in Titan's atmosphere in significant quantities. It is one of the key photochemical products of nitrogen-methane atmospheric chemistry. The tholins produced in Titan's atmosphere contain nitrogenous species, including the precursors to the nucleobases. Laboratory simulation of Titan atmospheric chemistry has produced nucleobase analogues. The specific yield and selectivity depend on the exact conditions: UV flux, temperature, gas composition. But the basic chemistry is established.
Titan is, in a specific sense, running the experiment of nucleobase synthesis under conditions similar to those that may have existed in certain prebiotic environments on early Earth. The difference, and it is important, is that Titan's environment uses methane as a carbon source rather than CO2 and has no liquid water at the surface. But at impact sites like Selk crater, where liquid water was transiently present, the combination of Titan's HCN-rich atmospheric chemistry with liquid water could, in principle, drive nucleobase synthesis at rates significantly above background. If DRAMS finds nucleobases at Selk, the question becomes whether they were produced there by impact-driven chemistry, transported there from the surrounding tholin-rich surface, or produced by biology. The chiral analysis distinguishes the last from the first two. The distribution across the crater structure distinguishes impact-driven from transport. This is why Selk is the target.
Not because Selk is uniquely dramatic or visually interesting, because Selk is where the specific experiment of water plus nitrogen-rich organics ran for thousands of years. Because Selk is where the specific molecules most relevant to life's origin have had the best chance to form. Let us now talk about what is happening in the broader scientific conversation about Titan right now, about the current state of research and what is being published and debated. Since Cassini ended in 2017, Titan science has not stopped. Cassini's enormous dataset is still being analysed. New papers on Titan's chemistry, geology, atmosphere, and potential habitability continue to appear regularly in journals including Nature, Science, Geophysical Research Letters, and Astrobiology. Among the recent significant findings,
new analysis of Cassini radar data showing previously unrecognized geomorphological features, possible lava flows of water ammonia from a volcanic vent system, strengthening the cryptovolcanism hypothesis, and the possibility of subsurface ocean material reaching the surface. Laboratory studies showing that specific tholin compounds can serve as precursors to cell membrane-like structures in liquid methane, suggesting that the lipid bilayer function essential to Earth cells might be replicated by different molecules in methane-based environments. Modelling studies of Titan's methane cycle using improved climate models that incorporate Cassini's final measurement campaign, improving predictions for what dragonfly will observe meteorologically and where liquid methane is seasonally present.
Analysis of the photochemical production rates of various organic species in Titan's atmosphere using improved photochemical models calibrated against Cassini's ion and neutral mass spectrometer data, providing better estimates of the surface tholin accumulation rates and composition over geological time. The scientific community working on Titan is active, productive, and growing. The anticipation of dragonfly, still a decade away from arrival but already driving research questions, is already shaping the scientific agenda. This active scientific community represents the institutional knowledge base that will analyze dragonfly's data when it arrives. These are the researchers who will know what the results mean within the context of decades of prior work. The continuity of Titan science from Cassini through dragonfly and into the future is one of the program's genuine strengths. Let us now talk about the specific and personally immediate thing that you can do tonight to connect with the Titan story, about what is visible and what it means, knowing everything we have discussed. If Saturn is currently visible in your sky, and it is visible to the naked eye for about 10 months of every year, go outside and find it. It does not twinkle the way stars do. Its light is steady, yellowish white, brighter than most stars. If you have binoculars, even 7 by 50 binoculars, the kind used for bird watching, point them at Saturn. You will see that it is elongated, not round. The rings create a stretched appearance even in modest magnification.
Galileo saw this in 1610 and could not understand it. He described Saturn as a triple planet because he lacked the magnification to resolve the rings as separate from the disk. If you have a small telescope, 80 to 100 millimeters of aperture at 50 to 100 times magnification, the rings become unmistakable.
The disk of Saturn is visible. The Cassini division, the gap between the A and B rings, is visible under good conditions. And near the planet, displaced to one side or another depending on its current orbital position, a small point of light. Titan. That point of light is currently experiencing weather. The northern hemisphere of Titan is moving toward its winter, the southern toward summer. Methane evaporation rates are changing. Cloud systems are forming and dissipating. Rivers are flowing from areas of recent rain toward the methane seas. And in a building in Laurel, Maryland, the Johns Hopkins Applied Physics Laboratory, where Dragonfly is being developed, engineers are working on the rotorcraft that will fly in that weather. They are solving specific problems. How to keep bearings lubricated at -179 Celsius. How to make the autonomy software make good landing decisions. How to ensure the heat shield survives the entry into Titan's atmosphere at 6 kilometers per second. The point of light in your binoculars and the engineering in that building in Maryland are connected. One is the destination, the other is the journey toward it. In 2028, Dragonfly launches. In 2034, it arrives. In 2034 to 2037, it flies. It samples. It measures. It sends back the most detailed information ever obtained about Titan's surface chemistry. And in 2037, we will know things about the origin of life and the distribution of chemistry in the solar system that we do not know now. Things that will reshape how we think about what we are and whether we are alone. The point of light is there every clear night that Saturn is above your horizon. Look at it, knowing what it contains. Go outside tonight. Find Saturn. It does not twinkle. Planets don't. They are close enough that their tiny disk averages out the atmospheric shimmer that makes stars flicker. Saturn's light is steady, warm, yellowish white. You can see it with the naked eye for most of the year, brighter than the majority of stars. Look at it for a moment. Right now, while you stand there, while the earth turns beneath your feet, while the night sky does its slow rotation, a moon is orbiting that planet. A moon with rivers, with seas, with rain falling from clouds in the orange sky. A moon where the chemistry that precedes life has been accumulating and preserving itself for 4 billion years. Titan, 1.4 billion kilometers away. We spent tonight making the case honestly, not as advocacy, as physics and chemistry and numbers and the actual lived experience of what it would mean to be there. Here is what those numbers say. The radiation on the surface of Titan is 5 to 6 millisieverts per year.
The radiation on the surface of Mars is 200 to 300. The difference is not cosmetic. It is the difference between living on a surface and living underground, between building habitats that face the sky and building bunkers that face the regolith, between the first generation of settlers accumulating a manageable career dose and the second generation accumulating a dose that raises cancer risk to clinically significant levels. Titan's atmosphere handles this. 1.5 atmospheres of nitrogen above your head doing what Earth's atmosphere does, absorbing, scattering, blocking. It does not care whether you have a magnetic field. It does not require engineering. It is simply there, a property of the moon itself, a gift from the specific combination of cold and size and chemical composition that makes Titan unique in the solar system. The atmospheric pressure itself changes the engineering. a suit on Mars must hold 0.3 atmospheres against near vacuum. It inflates, it stiffens.
It fights you with every movement of your hands. A suit on Titan manages thermal insulation against minus 179 degrees. A hard problem, but a tractable one. A problem in the direction of technology we understand. The suit can be flexible. It can move with you rather than against you. Daily surface work in a Titan thermal suit is different in character from daily surface work in a Mars pressure suit. That difference compounds across thousands of excursions over years of habitation. The flight. On Mars, Ingenuity, 1.8 kilograms, no payload, a few minutes per flight, made planetary history just by leaving the ground. On Titan, Dragonfly, 450 kilograms, a full mass spectrometer and science suite, 30 minutes per flight, 8 kilometers covered per sortie, is not the limit of what is achievable. It is a conservative first mission. Flight on Titan is not a technological miracle. It is the default mode of transportation.
And what flight means for exploration and for the lived experience of habitation, the ability to travel, to see different environments, to range widely across a varied landscape. This is not a small thing for people who live somewhere for years. The chemistry. Titan's surface is covered in organic compounds that have been accumulating for 4 billion years, preserved by cold, protected from UV by the thick atmosphere. Amino acid precursors, nucleobase precursors, the building blocks of biology, frozen in place since before complex life existed on Earth. At Selk Crater, where an impactor melted the water ice, where liquid water was in contact with this organic material for thousands of years, the specific experiment of water plus organics that may have started life on Earth was run and preserved and frozen. Dragonfly carries a mass spectrometer sensitive enough to read what that experiment produced. If the answer is biological, if DRAM-S finds amino acids in chiral excess, molecules showing the handedness that biology produces rather than the equal-handed randomness that abiotic chemistry produces, then the answer to the most fundamental question ever asked by science is no longer unknown. Life is not a singular accident. Life is what happens when chemistry and energy and time come together in the right configuration. The universe is full of it. If the answer is prebiotic but not biological, complex chemistry, amino acids and nuclear bases in racemic mixture, no sign of life, then we learn what 4 billion years of prebiotic chemistry looks like without the step to biology. We learn what conditions are necessary but not sufficient. We learn where the gap is, and we have a precise, data-driven picture of what more is needed. Either result is worth the journey. The rain is falling on Titan right now. Not metaphorical rain, not poetic rain. Actual methane rain, falling from actual methane clouds onto organic dunes in an orange nitrogen sky. Rivers are running somewhere in the haze. The northern seas are rippling with waves driven by gentle surface winds. The chemistry is continuing, as it has continued for 4 billion years, patiently, indifferently, producing complexity and accumulating it and preserving it. This is not Mars. Mars is extraordinary. Mars is important. Mars is the right first step, closer, more technically accessible, the logical next stop on the road outward from Earth. But Mars is a world of what was. Ancient riverbeds, ancient lake floors, the geological record of a world that had water and then lost it, that may have had life and then lost it. Mars is archaeology, fascinating, important, irreplaceable archaeology. Titan is a world of what is. The chemistry is happening now. The methane cycle is running now.
The prebiotic reactions are occurring now in the thin films of liquid that form in impact craters, in the tidal mixing of the subsurface ocean against the rocky floor, in the photochemical reactions in the upper atmosphere. If life exists on Titan, it is alive today, metabolizing, responding, present. And even if life does not exist on Titan, even if Dragonfly finds only prebiotic chemistry in all its stages of development but no biological signature, Titan is showing us the universe at a stage it no longer shows us on Earth. The stage before life. The stage that led to life. The chemistry that our own ancestors, our molecular ancestors, the first self-replicating molecules that would eventually become us, came from. Titan is the mirror of our origin, and we are, for the first time in history, in a position to look into it. Dragonfly launches in 2028. The engineers building it are solving specific problems right now: bearing materials, autonomy software, heat shield design, mass spectrometer calibration. They are going there because the scientific community looked at the solar system and said, that orange moon is where we need to go. That is where the question about life's universality can be answered. In 2034, the first images from Titan's surface, taken from a rotorcraft hovering in the orange haze, will show the world a new kind of landscape. Not rocks, organic dunes under an orange sky, perhaps a methane shoreline, perhaps the distant blurry disk of the sun through the haze. Those images will change the public imagination the way Earthrise changed it. Not immediately, not with a single press cycle, but over years, as people absorb what they are seeing, as the idea of a world with weather and rivers and organic chemistry settles into the collective understanding, Titan will become real in a way that no amount of orbital data has made it. And that reality will build the case for the next mission, and the mission after that, and eventually, on a timescale measured in decades, in the working lifetimes of children alive today, the case for sending people. People standing on Titan in a thermal suit, looking at an orange sky, feeling the gentle 0.14 G pull, hearing through their suit sensors the soft sound of methane rain beginning. That is not tonight. That is not this decade or the next. But it is not a fantasy either. It is a sequence of steps, each of which has a name and a budget and a team working on it. Dragonfly, a follow-on lander, nuclear propulsion development, a crewed mission concept. The sequence begins with tonight, with standing outside and finding that steady point of light that doesn't twinkle, with knowing what it is, with understanding that a moon with rain and rivers and organic chemistry and possibly life is orbiting that point of light right now. The sequence continues with Dragonfly in 2028 and the data from Selk Crater in 2037, and whatever those data say about the nature of life in the universe. And the sequence ends if we make the right choices, if we direct the right resources, if we maintain the kind of sustained scientific vision that has carried every great exploration program from concept to reality, with humans on Titan. Not instead of Mars, after Mars, as the next chapter in the story of a species that cannot stop looking outward. Go inside, but remember what is up there. The rain is falling, the chemistry is running, the answer is waiting.